legs, and we'll come back and we'll take care of experiment 10 a little bit later. Again, not a lot going on in experiment 10, actually. And this will keep us on track. Again, a couple of reminders as well. We do have a quiz coming up on Wednesday on titrations and buffers. Again, we'll do that at the beginning of lab on Wednesday, kind of like we did the first quiz. And we do have our next exam coming up as well, I think a week from Wednesday. So keep all that in mind as it stands right now. All right, so we're just going to wrap up the last few slides here from 16. And then, like I said, we will roll into 19, which is nuclear chemistry. And first off, though, is any questions on any of that stuff we were talking about in terms of KSP, how to calculate the effect of pH, common ion, concentration, and also how to selectively precipitate out things? And really that sort of last example that we did there is really sort of the basis of qualitative analysis, as I was talking about. You know, really in qualitative analysis, we do that sort of selective precipitation. We selectively kind of precipitate out certain ions that are floating around in the solution while keeping others basically still floating around in the solution. And then once we're done with those, we kind of continue on and precipitate out another kind of group of ions and keep the other ones really floating around in the solution as well. So really qualitative analysis is really just that whole kind of selective precipitation. And even within a group, we do that selective precipitation. We kind of precipitate out one individual ion at a time in a lot of cases. And, you know, using KSP allows us really to understand, you know, what the concentration of the ions need to be, what the things that should precipitate out and what you need to do, you know, in terms of things like pH, for example, and then those type of things to keep things from maybe not precipitating out. So any questions on any of that calculation part of the stuff that we were talking about earlier? So this is a table. Again, you have a similar one in your book, but this is basically, you know, our qualitative analysis table. And if you remember qualitative analysis, as we talked about before we started talking about group 1, and we did the groups 1 experiment, qualitative analysis are really groups of ions. They can be cations, they can be anions, but they're groups of ions that basically share similar solubility sort of properties. So for example, group 1, as we see there, which is silver, mercury 1, and lead 2, those guys all share basically the fact that they are insoluble in things like chlorides, bromides, iodides, and stuff like that when you think about solubility rules. So that's why we have the group reagent that we used in group 1, which is hydrochloric acid. Again, here the hydrochloric acid is a source of chloride, which is going to allow those precipitates to come out while leaving other groups sort of still floating around. So remember, really the whole idea here is if you had, say, group 1, group 2, group 3, group 4, all floating around in the solution, you know, when we add HCl to it, it basically is going to attack only group 1 ions that are floating around. And that's going to basically bring our group 1 ions down here as a solid, while group 2, group 3, group 4, we want to call it group 5 as well, you know, they're still floating around as ions. We could do some decanting, right? We have now isolated those 3 ions, and we could do some things to this to basically separate out each of these individual ions one at a time till we get to sort of specific groups along the way. Once we do that, we would then maybe go to group 2, which is some of these guys here. Hydrogen sulfide gas there is basically a precipitating reagent. It's basically a source of sulfide. But again, as we were talking about, what makes this important is actually acidic conditions. So again, that pH, which affects solubility, is really important, you know, when we're trying to separate out group 2 really from group 3. As you can see, it's the exact same precipitating reagent. The only difference is this is done in basic solutions. So again, as we were talking about through the calculations and stuff, it's that sort of control of pH, which is going to allow, you know, these guys which have similar sort of solubility properties, but the difference here, that pH, is going to allow us a place where we can basically separate out those guys from each other. So, things that we've been talking about again by pH and stuff like that, very important in terms of, getting group 2 out of the way first, keeping group 3 floating around and so forth. And then we get down to group 4 and 5, which are oftentimes together. And these guys are very soluble in a lot of things. So we have things that have pretty much solubility in everything. So we get to things like flame tests for these guys. There are some precipitations that we could do with carbonate to verify the presence of it. But really the whole idea here is, again, we could really focus in on each of these things. We could actually focus in on solving for chloride like we did with silver, and we could figure out how much HCl we would need to start seeing this guy precipitate out, this guy, and this guy precipitate out, based on sort of the KSP. So this is sort of a practical, useful application of KSP, is to allow us to figure out things like this. If we want to precipitate out certain ions, what concentrations we would need to do that, and things of that nature. Any questions on that there? Okay. And that's what you look like as you're going through the procedures for our different groups. And again, as we talked about, there's a precipitating group reagent and then obviously individual tests that we go through. And the nice thing is on some of yours is they got rid of a lot of those ions. You don't have to worry about it. But really, when we do get to that kind of group 4, group 5, a lot of those things that really, you not are soluble in a lot of things, we rely a lot upon flame tests, and flame tests can be very helpful when you're doing qualitative analysis, especially if you get to a general unknown, for example, where you're not really sure, what groups are present or things like that. Sometimes, a good thing to do is actually a flame test. Take a little bit of your sample, kind of prepare a flame test solution, and look for colors. And when you look for colors, that gives you sort of an idea as, oh, I saw some purple. Maybe I got some potassium happening there. I saw this kind of greenish bluish color. Maybe there's copper or barium present. And, a lot of times that's what people will do in person when they're running through a general unknown, is to kind of do like just a flame test, kind of see, what colors you might be able to see. And then obviously go through the procedures, and it kind of narrows you down and gives you an idea as to maybe what to look for as you go through it. All right. That should wrap chapter 16. Any questions on 16? A reminder as well that in 16, there is, I believe, the last part of 16, which I think is 16.3, I want to say. And that has to do with KF and complex ion equilibrium. We will come back to that. So it will not be part of exam 2, but we will come back to it in a later chapter after we do 21, I want to say, something like that. We'll come back and talk about that. So we're skipping it for now, that last little part of 16, I think, which is, again, the KF, or formation constant for complex ions, but we will come back to it a little bit later. Any questions on any of that there? Okay, so we're going to kind of switch gears here. And, the good news is, I don't think too much ice table is happening here in this chapter. So a little bit of different stuff here. So as we talked about at the beginning of this class, we're at the peak, and now we're going to come back down the other side. And again, we're going to get into some chapters here where it's more sort of formulas and that type of stuff. The really heavy conceptual part of it, we have just got past, which is obviously 15 and 16. And again, this will be a little bit more straightforward stuff here in these last chapters. We'll see some Ks and equilibrium, and we'll see probably some ice tables a little bit, but not as much in these sort of chapters. So this is chapter 19, which is nuclear chemistry, and as of now is part of the exam next week. So keep that in mind. So let's talk a little bit about radioactivity. So radioactivity is basically the spontaneous decomposition of an element into sort of smaller nuclei. They go through radioactive decay. Some do it sort of naturally. You could sort of get it going and starting that process as well. And nuclear sort of chemistry, a little bit different than regular sort of chemical reactions, in the sense that, as we will see in this chapter, regular chemical reactions really involves just sort of the rearrangement of the atoms. We don't really change elements, which is why we balance equations, right? Left-hand side, right-hand side. If I started with 4 carbons, I end with 4 carbons, maybe in different sort of things, but I have that sort of conservation. In radioactive sort of reactions and nuclear reactions, I guess is a better way of saying that, we get a lot of changing of the actual elements. They form new elements along the way, and that's because a lot of what we deal with here is kind of the particles we find in the nucleus. So that's your protons, that's your neutrons that sort of get changed, and that's different than in a chemical reaction where what we deal with typically is electrons sort of involved. So again, these sort of reactions are a little bit different than your traditional sort of chemical type reactions. When something does go through sort of this radioactive decay, where it starts in terms of that nucleus is sometimes referred to as the parent nuclide, and whatever is sort of forms as a result of that radioactive decay, is what is sometimes referred to as the daughter nuclide. All nuclides, which is a fancy word for nucleuses and atoms and stuff like that, is basically with 84 or more protons, basically are going to be radioactive. So a lot of what we deal with is on those bottom 2 rows actually on the periodic table, your lanthanides and your actinides, where you got uranium and all those kind of guys. So a lot of these guys get sort of involved here in nuclear sort of reactions. We usually in normal chemical reactions don't deal too much with those guys, but here we will deal with them. So let's talk a little bit about some different types of radioactive decay. And if you remember our good friend Rutherford, he did an experiment. That experiment involved something like alpha rays and gold foil, which was an important experiment, right, to determine sort of the structure of the atom. So let's talk about the different types of radioactive particles. Alpha rays or alpha particles, they have a charge of +2 and have a mass of about 4 AMU. They're basically the helium nucleus. So alpha particles are sometimes abbreviated a couple of different ways. Sometimes they use the alpha symbol and a 4 and a 2. Or sometimes they'll actually use helium and a 4 and a 2. So those are common sort of symbols that are used for alpha particles. Beta particles or beta rays are basically have a -1 charge. They're essentially like an electron. And also beta particles also have some different sort of symbols. A beta particle sometimes is used as an electron with a 0 on top, a -1 on the bottom, or they use the beta symbol with a 0 and -1 to represent that beta particle. A gamma ray is basically just pure radiation. So if you remember the electromagnetic spectrum, just past X-rays, you find gamma rays, short wavelength, very high energy. And it's kind of like pure energy, sometimes just abbreviated with the sort of gamma symbol, 0 and 0, sort of happening there. In addition, we'll see some other things along the way that might not be something you've seen before, perhaps. We can have something known as a positron. That's like an electron with a good attitude. And it also has the same symbols. Thank you for the courtesy laugh, if there was a courtesy laugh. And we do use actually the same symbols there as the beta particles, but it is +1. So, if you just see, just to let you know, if you kind of, how do you know which one's which? Probably if you just see somebody lay up just that symbol, they're probably referring to the beta particle. If they lay up just the beta particle and they want it to be a positron, they definitely will put the positive there somewhere to sort of indicate that. So they'll definitely kind of include that positive. And, and if you don't see it, it's probably a safe bet they're talking about the beta particle there rather than the positron. So usually with the positron, they don't kind of use these two sort of notations. Somewhere a plus will be kind of inserted to let you know that it is that. Some reactions, nuclear reactions, will undergo what is referred to as an electron capture. And as we will see, that is pretty much what that sounds like. It's basically an electron being added to something, like it's grabbing it, and then it will undergo a certain type of reaction. So you may be asking yourself, what are these numbers on top and bottom? And hopefully you remember, but just a reminder, that top number there is our good friend, the atomic number. Our bottom number is the mass number, right? So that's what those guys basically refer to. So just to remind you what those mean, just in case, the atomic number is the number of protons that you find in the nucleus of an atom. If it is obviously a neutral atom, it will also tell you the number of electrons. But a reminder that if you're asked what is the definition of atomic number, it actually is just the number of protons, not the electrons. So it's just number of protons. By the way, also a reminder, good 1A throwback here. That is the number we find on the periodic table. Up there on top is the atomic number, right? When we look at the periodic table. The mass number is the number of protons and the number of neutrons that we commonly see in an atom, or the nucleus of an atom. And the mass number and atomic number, why they are sort of important to each other is, again, if you take the mass number, which is the number of protons plus the number of neutrons, and you take the atomic number, which is the number of protons, and you do the big subtraction move there, protons will cancel and you get the number of neutrons. So if you take the top number minus the bottom number, that is typically your number of neutrons. Another way sometimes isotopes are given, like copper 64, that 64 number is the number, is the mass number in that particular case. What are isotopes? Also a good reminder, isotopes, hopefully you remember, is the same element, but they have different masses. The reason they have different masses is the number of neutrons. So they have different neutrons. Also a good reminder, since I put hydrogen up there, hydrogen is the only element that has only a proton and an electron and no neutrons, right? Everybody else has protons, electrons, and neutrons. So hydrogen does not have a neutron, just a proton and an electron. And that's why when we talked about acid bases, when we talk about H+, that is referred to as a proton, because in order to become positively charged, it had to lose its electron, and that leaves it with only a proton in this particular case, right? So if you look at the periodic table 1.008, there is written underneath hydrogen, and that is not the mass number. It is not the mass number. Let me just cross that out a lot. Again, the mass number is not found on the periodic table. I'm having fun crossing out a little bit more. All right, the mass number not found on the periodic table, a reminder, that is the atomic mass, which is not the mass number. So that's also a reminder. The mass number, the atomic number, if you're ever asked how many protons, electrons, and neutrons there are, those all should be positive whole numbers. And if you look on the periodic table underneath the symbol, they're pretty much not whole numbers, none of them for the most part. So they are definitely not the mass number, but again, they are the atomic number, the atomic mass, but you can find the atomic number on the periodic table. So only the atomic number can be found there on the periodic table, not the mass number in this particular case. Here are some of the common symbols that we see here in nuclear chemistry, some of which we talked about. A proton is another one that we commonly see. A proton with a mass number of 1 and an atomic number of 1 as well. And those are two very common symbols that are used. A neutron is also another symbol that we see a lot here in nuclear chemistry. And again, has the 1 on top and 0 on the bottom. And there's our electron, which is basically our beta particle, and our positron and our alpha particle that's here. So really important to make sure that you know those symbols. Is going to help you when you're writing these sort of nuclear reactions to be able to write those things sort of correctly. Any questions on those symbols there? And again, you may not always be given the symbol, may be given sort of the problem in words. So you need to, again, like I said, sort of understand, what symbol goes with those things. In terms of penetrating things like lead into your skin and tissue, different types of emitters will basically penetrate further. So when we talk about sort of radioactivity, we oftentimes talk about something being emitted or it's an emitter, and that means that basically that particle is being given off. So something like alpha particles don't go, whoa, lights and sound there. Alpha particles go about 0.01 into a piece of lead. You can see beta goes a little further, and gamma rays go very, very far. What does this mean? Well, it means if you're ever working with anything that's radioactive, it's really important to know what type of emitter it is, so that you can obviously give yourself the proper sort of protection. Some things require nothing really more than maybe some gloves and distance and stuff like that. Some things required lead. Some things require lead, plexiglass, and all kinds of stuff, to be working with. So it's really, really important to know really the type of emission in terms of those radioactive particles. Obviously, something that's a gamma emitter is going to give off a lot more, going to penetrate a lot more. And as we'll talk about later in this chapter, obviously minimizing your time around it is obviously a very good thing as well. But, some things require a certain level of protection in terms of radioactivity. Other things obviously require a little bit less. Here again, in case you didn't like the first 3 times we saw these symbols, here are those symbols as well. So we're going to talk about how you balance nuclear equations. So as I mentioned a minute ago, it's much more difficult and different than sort of a regular chemical reaction. So in a regular chemical reaction, we balance everybody by doing the coefficients, right? And that is because we have a conservation of the elements. So as I mentioned earlier, if we started with 4 carbons, we should end up with 4 carbons. In nuclear reactions, we don't have that situation occurring. So we actually start with a certain element and we end up with 2 or more different elements on the other side. We also end up with particles as well. So honestly, I'm lying to you. It's not super hard to balance these. It's actually a lot easier. So to balance these is a very simple sort of process. When you go to balance a nuclear reaction, you basically got to make sure that 2 things are correct. The first thing is when you add up all the mass numbers on the left-hand side of the arrow, it needs to equal all the mass numbers on the right-hand side of the arrow. So if we look on the left-hand side of the arrow here, we got 235 and 1. That's like a 236er. Plus our 138 on the other side, 96. And there is a 2 here, which means we have 2 neutrons. So that would return a 2 there. And if we add up everybody on the right-hand side, we end up with 236. This technically would be balanced in terms of the mass number. The other thing that you need to make sure of is the atomic number is balanced on both sides. So if we take the same guy, we look at the atomic number, which is our guys on the bottom. We got a grand total of 92 happening there. We got 55 and 37, and 2 times 0 is 0. And that gives us 92 on the right-hand side. And that would make this guy balanced as well. So this would represent really a balanced chemical equation. They're actually pretty simple to sort of balance. Having a periodic table is probably your good friend when you do these guys, to be able to look at it. So how would one of these problems be? So for example, if we took this guy here, 235, 92 uranium plus our neutron, we go our 138, 55 cesium, and maybe you're not sure what that guy is, but they tell you got 2 of your neutrons. So the approach that you would want to do in this case is, as we were just talking about, we basically have 2 numbers. We have the mass number and the atomic number. And when we look at the periodic table, again, you can find the atomic number up there. So that's really where you'd probably want to start in this situation. You would look on the left-hand side and go, I got 92 plus 0, which is 92 for my atomic number. You would look on the right-hand side there and go, I got 55 plus 0, which is 55. So if you did a 92 minus 55 for your atomic number, you would get 37. What you would then want to do is look at the periodic table and find number 37. When you find number 37, as you can see here, you will see RB, and that is what will tell you what the element is. And obviously you would know the atomic number from that. To find the mass number, we would take the same approach. We would go up on top there for the mass number, and that's going to give us 236 on the left. On the right-hand side, we have 138 plus 2, 138 plus 2, and that gives us 140. So do the same thing. You take 236 minus 140, and that really will give you your missing mass number, which is 96 in this case. And that is how you go about sort of identifying what might be missing in this particular case. Is I would go atomic number first, find the missing mass number. Question on that. Now, it's also important to note that probably in most cases, the missing sort of person, if you will be some type of element that you could find on the periodic table. It's also important to note that it may not be. It could be like a particle, like a neutron, a beta particle, an alpha particle, which you would be able to find on the periodic table because that's helium. But you may not be an actual element. A lot of times it will be, but could be a particle as well. So if you do want to, you're like, it doesn't look like an element, then think about what particle that might be missing in that particular case. Any questions on that there? So a couple other terminology words that we oftentimes hear about when we're doing these. So sometimes we talk about it does this through this type of emission, or it emits a particle. Any type of emission, or it emits a particle, goes through this type of emission. That means the particle will be on the product side. So when they're talking about that particle, you put that particle on the product side. Now, in terms of nuclear chemistry, we sometimes hear words like bombarded or electron capture. Those guys means those particles end up on the reactant side. So those are two sort of common words, if you will, or a few words that you sometimes will see in these processes here. So let's take a look at one here together to kind of see how it goes. So PO212 decays by alpha emission. Write the balanced nuclear equation for the decay of PO212. So a couple of things. We would start with PO. The 212 again is our mass number. We could go to the periodic table and find its atomic number. And if you do, bottom right of the periodic table, number 84 is its atomic number. Again, from the periodic tables where we would get that. Now, it decays by alpha emission. So the emission means it's going to be on the product side. It decays by our alpha emission. And again, you could use 4, 2, and helium. If you wanted to, you could do 4, 2, and the alpha symbol is perfectly fine. Plus, that is what we're trying to find. So again, here we would approach it by going atomic number first. So on the left-hand side, we have 84 for our atomic number. Right-hand side, we have 2, which means our missing atomic number is 82. And if we do that and go to the periodic table and find 82, you hopefully should see our good friend lead sitting there. That means that our missing guy is lead with an atomic number of 82. 82 and 2 gives me 84 on the right and 84 on the left. All that's left now is our mass number. Remember, it needs to be the same on both sides. So that's going to be 212 minus 4 on the right-hand side. That's a lot of math there. We'll go with 208 and hope for the best there. 208. And now we would have our balanced nuclear equation. Again, if we add up all the mass numbers on the left, 212, all the mass numbers on the right, 212, all the atomic numbers on the left, 84, and all the atomic numbers on the right, 84. Any questions on where any of those numbers came from, the process? So really not extremely difficult, as I mentioned, as I was joking earlier, it's not really extremely difficult to balance these. Really helpful, again, having a periodic table and, you know, just some simple math. The only thing you do have to worry about in these cases is if you do have some type of coefficient, like we saw in the previous one, like there was a 2 in front of the neutron, you do have to take that coefficient into account when you're adding up the mass numbers and the atomic numbers. Any questions on that? Okay, then just a little bit of the differences between a chemical and nuclear process, some of which I've touched upon, but just to remind you, in a chemical reaction, it's really all about electrons. So if you remember when we talk about bonding, or you talked about bonding in the previous class, ionic bonding and covalent bonding, it's all about electrons, right? Electrons either being transferred, electrons either being shared and stuff like that. There's really no change to the nucleus. So we never touch any of the protons, the neutrons, or anything like that. And that is very different in nuclear reactions. Nuclear reactions are all about changing what's happening there in the nucleus with our protons or neutrons, changing protons into neutrons, neutrons into protons. And as we will also see, one of the big differences between a sort of chemical reaction and a nuclear reaction is obviously we're playing with things like protons and neutrons in the nucleus. It involves a lot of energy to change those things, and that's why nuclear reactions usually gives off a tremendously more amount or greater amount of energy than a traditional chemical reaction will, where we're just playing with electrons, because we have to kind of go in there and really change what's going on in the nucleus. And obviously that requires sort of a big difference in energy that occurs between those things. So what is happening as we kind of go through a beta decay, a positron decay, and those type of things? So these are some really badly done equations because they're all messed up. So let me take a look here. So I think they're okay on your notes, but they kind of got a little thrown away here. So we'll just look at the top one here, 14,6 carbon going to our 14,7 nitrogen plus our 0 minus 1 and our beta. So this is a beta decay. Again, a beta decay, or the word decay, means that the beta particle is being given off on the right. That is 7 and minus 1 on the bottom, which is 6, to match the 6 that we have on the bottom on the left, 14 on top on left, 14 and 0 on top on the right. These little sort of those guys there, those are neutrinos. They really have no mass or anything like that. We don't really deal too much with those here. So you don't have to worry too much about those or put them into the equations or anything like that. You don't have to worry too much in terms of that. What is happening here is we actually see a decrease in the number of neutrons by 1 and also an increase in the number of protons by 1. So the overall reaction that's happening here is, I'll write it down here, is we're taking a neutron in this case, and we're really converting it into a proton and a beta particle that's being sort of developed. So we're taking one of these neutrons and it's basically being converted into a proton and a beta particle. That is why we actually do not see a change in the mass number. So you're like, hey, we're taking away a neutron. Shouldn't we see a change in the mass number? So if we just kind of go through the process here as to why we don't see that, is we're going to take away a neutron, right? So this guy is going to lose a neutron basically, which if we did that, basically we would come to 13 carbon and 6, right? But the process though then results in a proton being made, which again is going to put that back in and guess our mass number, which is protons and neutrons. And that's how come it gets back to there. This guy then becomes 7, and now we get to basically nitrogen along with our beta particle that is given off. So although we lose a neutron in this process, we do gain a proton, and because the mass number is protons plus neutrons, it basically, this goes down, but this goes up, and that means the mass number actually will stay the same. So that's why we don't get a big change or anything in the mass number when we're dealing with a beta particle. On the bottom is a positron emission. And again, I'll just write the top one here. I think it's okay on your notes. Just all these arrows got all messed up here. And again, a positron is basically like a positive electron. It has the +1 that's here instead of a -1. And same thing that's sort of happening here. We again don't really see a change in the mass number, and that's for the same reason. We are losing a proton, but that proton is being changed into a neutron, and we're getting that beta particle or positron particle to basically come out. And the same thing happens here again if we sort of follow the trail here. 11,6 carbon loses that proton in this case, which technically takes him down to 10 and 5. And again, at 5, it technically becomes boron, right? But then it gains that neutron. And at this point, it then becomes 11, 5, and boron because of that. So again, ultimately, it doesn't change, but there is a change that's happening. We're losing a proton and gaining a neutron in this particular case. But the grand tally of everything, we don't see a change in the mass number. Any questions on that there?
Could you explain that part of like how they lose the, I think it's the proton, and then it goes back to 11 up top on the
Yeah, so this is this process as it's decaying. There's some transformation that's occurring and energies involved and things like that. And sometimes even collision with other protons, neutrons, and stuff can cause this to occur. But what's happening is we're basically starting with, say, on the top one, carbon that has a mass number of 14, which basically means that it has 14 protons plus neutrons total, right? And what happens in a beta decay, what ultimately is happening is we're first losing a neutron. So the first thing that's happening is this neutron through this process, and involves energy and some other things we'll talk about. But through this process, what's essentially happening is we're transforming a neutron into a proton, basically. And that process occurs by losing, basically, a neutron. And when it loses a neutron, if we just do the math of that, we basically end up with 13 up on top and 6 still on the bottom. And so it's still carbon at that point. It just lost really a neutron, which is basically one of these guys. But through that process, this neutron is really converted into a proton at that point, which means it then gained a proton. Which if we do the math on that, this guy then at that point, if you kind of do it step by step, has gained a proton, and now he's got to 14 on top and 7 on the bottom, and now he has changed to nitrogen in this particular case. And ultimately, though, when we look at sort of the big picture, he started with 14 in terms of the mass number. It actually ended with 14 in terms of the mass number. And you may think, well, nothing really happened in that case. But actually, something did happen. We actually lowered the neutrons by 1, but we gained 1 proton. So that sort of change that occurred basically canceled each other out. And overall, it looks like nothing has happened in terms of the mass number. But if you kind of do it step by step, which is, I guess you can kind of look at it that way, there is actually stuff happening in this process. So sometimes people look at it and go, oh, the mass number didn't change, so there's nothing really happening. It just sort of happens. And the way we sort of transform under those conditions, or when these conditions happen, this neutron into a proton is it gives off this radioactive particle, which is known as a beta particle, is basically given off from the nucleus as a result of that process occurring. Questions on that?
Okay, that makes sense. And then when you're like at the beginning, when we lost a proton, or was it that we lost a proton or a neutron at the very beginning of that?
At the very beginning, you can kind of think about it like in the nucleus, right? There's this neutron that's floating around,
Okay.
and there's something that's going to happen to it that's essentially going to allow it to kind of transform itself into a proton in the nucleus. And the result of that is, in part of that process, when that occurs, it sort of will emit off a beta particle from the atom. And that's why we say, you know, the beta particle is being emitted like a product. And I don't want to say it's not really like a chemical reaction, because, you know, but it's sort of like that. Like this is, you could kind of think about it as like a reactant, and then the proton becomes like the product that's being formed along with this guy that's being given off. So that process sort of occurs. Sometimes it occurs naturally. Sometimes you can sort of help it occur by shooting things at it, like neutrons, protons, or alpha particles. But that process is sort of taking place within the nucleus, where we're essentially losing a neutron in the sense of it's going away, but it's sort of being transformed into a proton. And a byproduct of that transformation is it will give off this radioactive particle known as a beta particle in this particular case.
And so that's why it stays as a carbon, because we're losing that neutron rather than losing like a proton or something.
Yeah, so at that point, it's still wherever I was, it's still a carbon at that sort of moment in time, if you will. And again, it doesn't actually happen just like this step by step, but you know, the first thing that happens is sort of the neutron is being lost or sort of being transformed. So at that particular point, we just lost the neutron, and it still has 6 protons at that point until very, very quickly, obviously almost instantaneously, right? We get this proton that's formed. And at that point, as a result of that neutron sort of transforming, we are now in a situation where we have 7 protons in that nucleus at this point. And then at that point, it's technically no longer really a carbon atom, right? Because 7 protons represents a nitrogen. So it's sort of how it gets transformed into a nitrogen and a new element, right? And it's because the number of protons, which is the atomic number, is the most important thing when we're talking about what element, right? Because if you look at the periodic table, every single element has its own atomic number. There's no atomic number that repeats. So although I kind of wrote it in this like step-by-step fashion, obviously this all occurs very quickly, right? So if you kind of break it down sort of step by step, up in that point where we kind of think about losing the neutron, it still has 6 protons, but very, very quickly we're going to form that proton as a result of that neutron disappearing. And then that's going to give us a grand total of 7 for our protons. And at that point, technically, once that sort of proton appears, if you will, we're at nitrogen at that point because we have 7 total protons that are present.
Okay, thank you. That makes sense.
You're welcome. Other questions on that? Again, like I said, obviously this is occurring very quickly. It's not like a step by, you know, slow type process. But if you just kind of want to follow, because it sometimes confuses people, like I was saying earlier, when they look at a reaction like this, they're like, well, I started with 14 and then I ended with 14. So clearly there's really nothing happening because that number doesn't change, but there really is a lot sort of occurring to keep that number at 14 in this particular case. All right. Some of our other sort of reactions, and again, we'll just look at a couple of these here. I'll just rewrite them so we can kind of see them sort of clearly. If we look at our argon here, and this is an electron capture. So we see the electron on the reactant side, and again, it forms 37 and 17 here. And what's happening in this case is we're going to take a proton, we're going to basically add an electron to it. And if you just add up the numbers, you end up with a 1 and a 0. That's going to create a neutron that's happening here. So in this particular case, we're basically making a neutron. I think I wrote the wrong number there, 37 up on top. Sorry about that. So 37 on top, 18 on the bottom there. And again, here we see sort of the same thing we were talking about. At this point, we have, I don't want to write 13, try 37, 18, argon. At this point, we're going to actually gain an electron, just like we see. That's going to then at that point turn this into 17, right? 18 minus 1. And then again, nothing's happening. And here, even though really something really is happening, our proton is being transformed into a neutron. So overall mass number still stays the same on the left-hand side and right-hand side. But what's truly happening is we're losing one proton, but we're gaining a neutron. So again, as it goes down, it's going to go back up because the mass number is our protons and neutrons. Alpha decay is really the biggest change that we see happening here. Giving off our alpha particle, which is really the helium, or again, you can use the alpha symbol if you like, and our 208-82 lead like we saw, that's happening here. And there's also something referred to as sort of spontaneous fission, and that is when we basically have something that will just automatically basically decompose into two new elements. So we have 252.98 californium, and that's going to decompose into 125.49 125.49 IN, and there's two of them plus some neutrons here. And this is a very popular sort of reaction in nuclear chemistry, which is known as fission. This is spontaneous fission, which means this guy is unstable, right? It's got 98 protons. So just naturally, it's going to basically break apart. And fission is a reaction where typically what happens is we start with something that's unstable. It will typically break apart into two new nucleuses and give off some neutrons, which is a very common thing. Also, a lot of energy involved usually in this process. So this is a spontaneous fission reaction where that occurs. There's also fission reactions, which we'll talk about, where you could basically start that reaction. And that's sort of the basis of like nuclear power, for example, nuclear power plants. Or nuclear fission reactions. You could actually start that by shooting something at it, like a neutron or something like that, to kind of kick off that sort of reaction to occur. So as we'll talk about a little bit later, they use sometimes uranium. They shoot some neutrons at uranium. It makes uranium very unhappy, and an unhappy, unstable nucleus or isotope, and it will go through this process. Does it always form, as we'll talk about later on, the same elements? It doesn't actually. So it doesn't always form the same two elements, but what it usually will always do is form a couple of elements that are new. Will always usually form some neutrons, and always usually accompanied by a good amount of energy that's sort of happening in that process. Okay. So here again, it's just a table, and I believe you have a similar one in your book that sort of describes the different reactions that we just talked about and those particles that are sort of giving off in those processes. So let us take a look at this one here, potassium 40. Again, when it's written like this, potassium 40, that 40 is the mass number. How do I know it's the mass number? Because if I didn't know that and I look at the periodic table for K, I will see 19 written up on top, and I will see 3910 like on the bottom. And again, I know from the periodic table that the atomic number for potassium is actually 19. So we're going to do potassium 40 up on top, which is the mass number, 19 on the bottom. This is going to go through, again, a positron emission. The emission means that that particle will find itself on the product side. And you could do the positron like this with the beta symbol. You could use the E symbol as well, but it is the positive version of it. So we want to take the same approach that we talked about earlier. We want to start with the atomic number. So to figure that out, if we look at the bottom here, I got 19. We look on the right, I got 1. If I subtract those two, that gives me 18, which is my atomic number. And that number is important because I could go to the periodic table, and number 18 on the periodic table there is our good friend argon. That leaves me the mass number. So up on top, I got 40. Over here, I got 0. So that makes the math pretty easy. So 40 minus 0 is 40 in terms of the missing symbol. And that would represent our balanced nuclear equation there. And our guy would be argon, 40 for the mass number, 18 for the atomic number. Any questions on any of those there or that one? All right, so now that I've done some, why don't you do these 4 here? Write the balanced nuclear equation for each of the following. So take a few minutes, and then we'll talk about it again. If you got a periodic table, it obviously would be very helpful to use. Take a few minutes, and we'll talk about it. Tells us we're dealing with this guy, or again, you could use that symbol if you like. Emission tells us that particle is going to be on the product side. Uranium-238, again, that's going to be our mass number here. So we will start with our uranium-238. We can find the mass number on the periodic table, and that looks like at the very bottom there, 92. Again, going to emit our alpha particle, whichever way you want to represent that. Missing atomic number is going to be helpful here. So on the left-hand side, I got 92. Right-hand side, I got 2. If I subtract that, that is 90. Again, I would go back to my periodic table and find number 90. It looks like TH. What's left at this point is our mass number up on top. So that's 238. And on the right-hand side, I have 4. So again, if I subtract those two numbers, that's going to give me 234 there. And again, this would be our balanced nuclear equation. Any questions on that one there? Same approach here for the second one. Emission going to be product side. Beta, again, you could go electron looking. You could use the actual beta sort of symbol there. So neon 24, again, being the mass number at the periodic table, we find the atomic number is 10. Given off our beta particle there. Now remember that this is negative on the right-hand side, so that's going to be 10 minus 1, which basically means I need to go actually 1 more to balance that out to 11. 11 and minus 1 is 10 on the bottom and 10 on the left-hand side. Number 11 on the periodic table is sodium. Going up on top, 24 on the left, 0 on the right, going to 24s there on the right-hand side. Any questions on that one? Positron emission. So positron, remember, is our, just like beta particle, but again with the positive symbol or number. Nitrogen 13, so that's going to be nitrogen 7 from the periodic table for our nitrogen. Also an emission, which means it's going to be on the product side. And in this case, 7 minus 1 going to give us 6. 13 up on top. And again, if we go to periodic table, number 6 is carbon in this particular case. And lastly here, this is an electron capture. So electron is this symbol. Capture is important. That means reactant side. Again, the only other word that pretty much means reactant side is if somebody says you bombarded it with like neutrons or something like that. So what we would actually start with here is beryllium, which is 7 for the mass number. Atomic number from the periodic table is 4. And again, because it's an electron capture, our electron would be on the reactant side. In this case, we just need to add what's on the bottom. So 4 and minus 1 going to give us 3 as our missing atomic number. Number 3 from the periodic table is lithium. Up on top, 7 and 0 is 7 And that would get us our balanced equation. Any questions on any of those? How to write balanced equations, figure out what's missing? Any questions on how to do those there? Okay, so the next thing we're going to talk about then is stability. And how do we know, for example, if this thing is going to be a stable nucleus, is it not going to be a stable nucleus? So the way that we determine that is there's a few different ways. A very popular way is what is sometimes referred to as the N to Z ratio. N being neutrons, Z being atomic number. So this is basically neutrons to protons ratio. And if we calculate the N to Z ratio and it's too high, neutrons will be converted to protons, and that will happen through a beta decay. So if we determine this ratio is kind of too high, we will go through a beta decay to basically bring the ratio kind of back down to a more acceptable level. And it will result in, not necessarily a perfect ratio, but it will be much better than it was before. If we do the neutron to proton ratio and it's too low, we're actually going to convert protons to neutrons via positron emission or an electron capture, or via a alpha decay, but not as efficient. So we really won't use alpha decay here. It will either go through a positron emission or an electron capture. And you may say to yourself, won't that give me two different things? And the answer is it actually will not. So if we look at the one we just did, which was this guy here, our beryllium, with our electron capture, gives us 7, 3, and lithium. So that's an electron capture. If I did my same beryllium, but did a positron emission, that means I would end up with this deal, which would then be 3 and 7 and lithium. They result in the exact same thing being formed, either a positron emission or an electron capture. So that's why you got kind of that option there for something that is too low in terms of its ratio. So it could go through one of those two things. The end result, as you can see, is the same guy being formed in that particular case. Any questions on that there? So you might be asking, how do I know if it's too high or too low? Well, how do we know if it's too high or too low? There's something that is referred to sometimes as the valley of stability, or depending on your book, the belt of stability. Use whichever one you like there. If you like belts versus valleys, you could do that. But this sort of yellowish sort of deal here is the valley of stability or the belt of stability. So when we talk about something being sort of too high or too low, if that ratio is too high, it means it's to the left of it, if you will, and it will go through a beta decay to bring that ratio again towards the valley of stability. While if something is too low, it will go through, like we just talked about, either an electron capture or a positron emission. And what that will do is bring the ratio up towards the valley of stability in that particular case. So what determines if it's sort of too high or too low? Well, we look at the atomic number. And if the atomic number is between 1 and 20, an acceptable stable ratio is a ratio of 1. If you're between like 20 to 40, an acceptable ratio is 1.25. If you're 40 to 80, the acceptable ratio is 1.5. And if you're kind of greater than 83, there is no acceptable ratio. You're probably radioactive. So a couple of things about these cutoffs. There are some obviously some gray areas, I guess is the way to refer to that. You can see this one goes to 20, but yet this one starts at 20. So if you're kind of in that 20ish range or something like that, some people will say, well, it's not 1, but maybe it's like 1.1, but it's not 1.25. So it's maybe okay. So there are some gray areas in between these. Obviously, you see that one stops at 40. This one stops or starts at 40 in terms of that. So to take away the gray area, just understand there are gray areas, and some people will maybe not do it this way. But for us, just to keep it simple, we're going to use these cutoffs as sort of hard cutoffs. And again, some people don't do that, and some people, find those sort of gray areas in between. And what I mean by that is if we're doing something between 1 and 20 and the ratio is not 1, then it either is less than 1 or greater than 1, even if it's just slightly over 1. And maybe some people will say that's okay because of this. We're just going to make it very simple. It either is that number, or if it's not that number, it's too high or too low. But keep that in mind that, some people, there is that grayish area between these guys that they'll say, it's actually okay because it's kind of close to 1, but, or maybe close to 1.25, but it hasn't really been a big difference. So I hope that sort of makes sense. So again, for us, just a straight hard cutoff on those numbers, and to keep it simple, either it is or it's not that number. So let's take a look at one to sort of see what's going on here. All right, so once you give it a try here, looking at magnesium 22, is it stable? And if it's not stable, what type of decay process will it undergo? And why don't you write the reaction? So what type of decay, and write the reaction that occurs. So take a minute or two and see what you come up with. So magnesium 22, which is the mass number. Again, the atomic number there can be found on the periodic table, which is 12. That means that the number of protons would equal the atomic number, which is 12. Our number of neutrons in this case would be our mass number minus our atomic number, which is 10. And that means that we would do our N to Z ratio by taking 10 divided by 12. And if we do 10 divided by 12, that is going to be a ratio of 0.83333. Now, this is atomic number 12, which means a proper ratio would be 1 of 1 is an acceptable ratio. So a stable ratio would be 1. In this case here, our N to Z ratio is less than 1, right? So it is too low. So we're here, we need to bring it up basically to a much better ratio. That means that it will go through either, in this case, when it's too low, either a positron emission or an electron capture. So remember, this is the one where it's too low. It could do one of those two things. So if I started with, say, the positron emission, we would write our equation like we've been doing on the other ones. Again, positron emission, going to put our positron particle on the right-hand side. Going to end up with an 11 for the atomic number. And that means that that is sodium. Up on top would be 22. Remember that if you did the electron capture, you will end up with the exact same outcome. Again, 12 minus 1 is 11, and 22 gives you sodium. Now, is this better? Well, it didn't ask us to do this, but we could check to see if we actually ended up in a better location than where we started. And if we look at the number of protons in sodium, that's 11. Number of neutrons in this guy would be mass number minus atomic number, which would be 11, which means we have now moved to a neutron to proton ratio of 1, which is actually perfect in this case. Does not always occur this way. It does not always occur that, by going through this process, you hit the perfect ratio. You should, though, see it move in the right direction. So you don't have to keep doing this process until you hit the right ratio. But once you do the process once, like the equation here, if you don't hit the perfect ratio, which doesn't always happen, it should at least be moving you in the right direction towards that belt of stability or valley of stability. Any questions on that one there?
The perfect ratio is 1, is what you're saying?
It is in this particular case, and it's based off of these. So it's based off
Oh,
of the atomic number. So when we look at magnesium, it falls into this range. And for guys in that range, the perfect ratio is 1. If we were doing something that maybe had an atomic number of 30, the perfect range would be actually 1.25. So it depends on the atomic number and sort of where it falls into one of these 3 spots, as to sort of what you'll use as your sort of perfect ratio for that sort of guys. And it's based off of the atomic number. Other questions on that? All right, why don't you try one more and see what you come up with. So why don't we do the same thing here? Is krypton 85 stable or radioactive? If it's not, then what way will it go through? And then also write the balanced equation here. So take a moment or two, and then we'll talk about it. Okay, so let's take a look at this one. So same approach here, looking at stability. So probably our neutron to proton ratio is good. Same thing, we want to kind of figure out what those numbers are. So again, 85 being our mass number, we could go to the periodic table there and find our atomic number, which is 36. So obviously that 36 tells us we do have 36 protons. Again, taking our mass number minus our atomic number, giving us our number of neutrons of 49, we'll go with. So that gives us our N to Z ratio here of 49 divided by 36, looking like maybe a 1.36. So we do want to determine, hey, is that good or bad? So again, we look here and we do see that the atomic number is 36, which means that does fall between the 20 and 40 range. And for that range, the acceptable neutron to proton ratio is 1.25. Technically speaking, like I said, some people will say between 1 and 1.25. But again, for us, we're just going to kind of keep it just a hard cutoff. Either it is or it isn't. So we'll kind of eliminate some of that gray area. But in this case, it actually is going to be too high in this case. And that means that because it's too high, it will go through a beta decay, right, to bring us back down. So if you kind of think about the belt of stability there, we're kind of over here. We want to kind of bring it back down through a beta decay. And if we do that, we would have 8536 krypton, giving us a beta decay here of that guy. And again, our missing would be 36 on the left minus 1 on the right, which means we actually need to go, one higher. 37 and minus 1 is 36. So 37 is RB. Up on top, 85 on the left, 0 on the right, 85. Question on that particular one there. So again, in case you're curious and you do come across it, like I said, some people in that grayish area, because 20 and the other one ended at 20, would say anywhere from 1 to 1.25 would be sort of acceptable. But that means if you are lower than 1, then it would technically be too low. But again, for us, we're going to use it as sort of a hard cutoff. But again, there's some of that grayish area, as you kind of get in that range as well. So just to avoid that gray area, we're going to use those cutoffs as hard cutoffs just to make it a little bit easier. But do keep that in mind. People will say, like I just said, that either one of those would be okay. Did it actually get us perfect? Let's see. So if we look at the RB, That means we have 37 protons. Neutrons in this case would be 85 minus 37. So that would be 85 minus 37, gets you 48 in this case, which means our N to Z is 48 divided by 37, which is about, we'll call it 1.3. So if you remember, we started at 1.36. By going through this process, we ended up at 1.3. Again, not perfect, but we are moving in that right direction in terms of the ratio. Question on that there. Our question, how to use neutron to proton ratio to figure out stability. So just to finish up talking a little bit about stability here, there are some other things that people sort of look at in terms of stability. Although neutron to proton ratio is a pretty good one, pretty common one that people use for stability, there are other things that people look at in terms of just in general, you know, do you have even numbers of protons, even numbers of neutrons, and things of that nature. And what we can see on this table, and you have a similar one there in your book, but when we get sort of an even number of protons and an even number of neutrons, you can see how many sort of stable nucleuses there are. And that's sort of your best situation. Your next best would be like even protons, odd neutrons, still not too bad. Next best would be odd protons and even neutrons. And your worst situation in terms of stability is when you have sort of odd number of protons and an odd number of neutrons. That's sort of the worst one. So sometimes people might not calculate the N to Z ratio, but just look and go, oh, that's even and even, then that's a really good stable situation. Or that's odd and odd in terms of protons and neutrons. That's not such a normally good situation that occurs. Also, in addition, if the number of nucleons add up to a magic number, it's more stable. Nucleons is a word that we'll hear a lot of in sort of nuclear chemistry, and nucleons is, as it sounds like, the particles found in the nucleus of an atom, which, as you hopefully know, are your protons and your neutrons, right? So when we talk about sort of nucleons, that's sort of what we're talking about. Basically, like your mass number, it's your number of protons and neutrons is what we're talking about. So kind of like how things try to get to sort of noble gas configuration through bonding, is the same idea here. Things are really a lot stable when we have neutrons or protons that have either 2, 8, 20, 28, 50, 82, and your mega number there is 126 for neutrons. And then again, that's sort of like, you know, 10, 18, 36, 54, and so forth for our noble gas configuration. So I say most common neutron to proton ratio is commonly done. Next kind of most common is kind of like looking at it. Do we have even, odd, you know, type of situation in terms of stability. Any questions on stability or how to figure it out? Okay. All right, so we will lay up the lecturing there for now. We've got a good little jump into 19, put us a little bit back on track, I hope. So what we'll do is, since we